Hello friends, welcome to the channel Physics by IITians, where we learn and understand physics to crack examinations and interviews related to physics. So today I shall discuss a very important topic and I shall introduce to the concepts of waveguides. So please friends, watch these videos very carefully till the end to get the full benefit of this video. So today I shall discuss about the origin of transverse electric modes or transverse magnetic modes or TEM modes, that is transverse electromagnetic modes. Whenever we are talking about the propagation of the electromagnetic waves between two parallel conducting plates, what will happen? What will be the nature of the electromagnetic wave? Which kind of interaction is going to happen with the boundary or at the boundary, and what are TE and TM modes, how they are generated. So let's start. So before that I want to tell you what is the waveguide. The waveguide is a structure that is consisting of highly conducting walls in the form of a long open pipe that is used to guide electromagnetic wave in the microwave region. Microwave region around 3 to 300 gigahertz from one place to the other, and such a structure is called waveguide. So why we are choosing conducting walls? Because in the earlier video, that is latest video, I have discussed already that conductors are good reflectors of electromagnetic wave at certain frequencies. So we are using waveguide, we are using conducting walls for as a reflector, and the waveguide is usually used to guide the electromagnetic waves in the microwave region, that is large higher frequency. In the lower frequencies we use transmission lines. So why do we use waveguides? Waveguides we use for the transfers of signals without minimum losses. I mean having minimum losses or without distortion of the signal. That's why we are using. The common example is the uh, fiber optics. I mean optical waveguide. We use fiber to guide optical signals, and we are getting benefits of optical fiber in terms of the internet. Okay, so this is a very important topic, that how we get the concepts of transverse electric and transverse magnetic modes. So before describing, I want to tell you that we have to first remember that whenever we are confining the electromagnetic wave within a boundary, that is within a particular direction, then we know the electromagnetic wave, transverse electromagnetic wave, which we think at the free space, for the free space they are transverse and they are perpendiculars to the electric and magnetic fields are perpendicular to the direction of propagation, that is electric field and magnetic field E is perpendicular to B is perpendicular to K. All are mutually perpendicular to each other, and we describe if this is the electric field vibration and if this is the magnetic field vibration, the propagation will be perpendicular to both the directions. But this is the case for the electromagnetic wave that is traveling in free space. In here, you are confining the electric field or electromagnetic wave within certain boundary. So there will be, the case will be different, and that's the origin of your TE and TM modes. Now we'll look at how is it so. So we shall discuss that. We shall consider two perfectly conducting plates located at y equals to 0. Suppose this is at y equals to 0 and this is at y equals to a. Now suppose this, you are considering that the electric field will be somewhere, you are assuming that electromagnetic wave, so you have to define the direction of the electric field and direction of the magnetic field. The propagation will be certainly parallel to the uh, uh, conductors, because the boundary, at the boundaries, that is at y equals to 0, at y equals to a, the electric field vector, that should be 0. There should be no electric fields at that boundary, and the light should be reflected at the boundary, not the light, in this case this is the electromagnetic wave, it should be reflected at the boundary. So what will be our boundary conditions? So boundary conditions will be that we should, the B magnetic field vector, that is perpendicular component of the magnetic field vectors, that should be continuous, and parallel components of the electric field vector, that should be continuous, and electric field electric field vector, the parallel field component, that should be 0 at the boundary, which I have already told you, and magnetic field vector, that is perpendicular vector component, that should be also 0. Now due to these boundary conditions, we are defining our, suppose this we have to take the two cases whenever the electric field is the parallel to the perpendicular to the direction of propagation, and another case is that electric field is magnetic field is perpendicular to the direction of propagation. So what will happen in the both the two cases? The for such waves there are two possible polarizations. One is the electric field along the x-axis, because I am defining my conductors plates are along y and z, yz plane. Okay, so the perpendicular direction is along the x direction. So I have two cases, whether electric field is parallel to the x direction, that is along perpendicular to the plane, perpendicular to the conductors, and whether this h is parallel to the x direction. So whenever E is parallel to the x direction, hx will be 0, there will be no magnetic field. Whenever h is parallel to the x direction, then Ex will be 0, that is there is at that point direction there is no electric field. So these two directions are called, whenever the electric field is perpendicular to the direction of propagation, we are calling the wave as transverse electric wave or TE wave. Whenever we are discussing or we are showing that magnetic field is parallel to x direction, or magnetic field is H is perpendicular to K, then that wave will be transverse magnetic wave or TM wave. The transverse word is used to denote that the field, that particular field is transverse to the direction of propagation. Or transverse means the direction which is perpendicular to the planes, that is plane of the conductors, and the directions which is parallel to the plane of the conductors, that is the longitudinal direction or the axial directions. Or in certain occasions we can get transverse electromagnetic wave, that is the electric field and magnetic field both are perpendicular to, mutually perpendicular to the k, that is propagation vector. We will then give the name, that is transverse electromagnetic wave. And in certain cases also there will be the components, all the components are non-zero along the direction of propagation. So the waves which are confined in certain boundaries, that are not the usual electromagnetic wave which we discuss, that is propagating in case of free space. Now here look at the let's find out the nature of the wave. So suppose let us consider an electromagnetic wave with frequency omega and wave number k is in the yz plane, and it is incident at y equals to a plate. Okay, so you have y along this direction and this is along z. So y is this is y, this is z at y equals to 0 and y equals to a. You are thinking that, you are imagining that there is an electromagnetic wave which is incident at y equals to a plate and at a certain angle theta. And now x and z are physically indistinguishable. Okay, so this is no generally, y and z are physically indistinguishable because this is also conducting plates and here is also conducting plates. So for the light, whether it is incident along this direction or it is reflecting from this direction, both are the same, both the plates will behave the same for the electromagnetic wave. So there is no generality loss. This is not x, this is y. Okay, the wave incident on y equals to a will get reflected because the electromagnetic wave, the at y equals to a, this is the our conductor, so it will reflect it from the conductor. So from reflection, after reflection it will again reflected from this end, after reflection this will again reflected, this will again reflected. So there will be several or multiple reflections occur, and this wave will propagate parallel to the plane, that is along yz plane. So let's find out the nature of the wave. The electric field in the region between the two plates is given by the sum of the incident wave and sum of the incident wave and reflected wave. So we have to show that, suppose this is the our diagram, this is along z, and this is along y. So you are taking your electric field, that is the electromagnetic wave is incident along this direction and it get reflected along this direction. So we are defining that the electric field at the boundary should be the sum of the incident electric field plus sum of the reflected electric field. So we shall find out the components, that is incident component of the electric field and reflected component of the electric field, these two. So electric field in generally we can represent it I cap E naught prime e to the power j k dot r minus omega t plus I cap E1 naught prime e to the power j I k1 dot r minus omega t. We are taking here for transverse electric field. So we are denoting the, for the incident electric field, the magnitude of the electric field is E naught prime, and for the reflected electric field the magnitude of the electric field is E1 naught prime, and we are taking the direction of propagation, that is propagation vector for the incident as k and propagation vector for the reflected electric field as k1. Now we all know that the reflection perfectly conducting medium, the amplitude will be exactly equal with the opposite sign. So E naught prime will be equals to E1 naught prime. So what does it mean? This means that the same amplitude but a phase angle of phase change of pi. Now after putting the values we get that E field, that is the electric field, will be at the boundary, it should be I cap E naught prime into e to the power j k dot r minus omega t minus of e to the power j k1 dot r minus omega t. Now we will find out the two unknown values, that is k dot r and k1 dot r. Now this is the transverse electric field. So the electric field components, it is incident along this direction. So this have two components, one along the z direction, another along the y direction. So to find out the k dot r, we split it into two components, which is along this y direction and along the z direction. So along y direction this is k cos theta for the k component, and along z direction this is k sin theta. So k dot r will be k cos theta into r, means here it will be y, and k dot r for the y component, for the perpendicular z component will be k sin theta and r will be z. So k dot r will be k cos theta y plus k sin theta z. Now similarly we discuss it, or we consider for the k1 case. What will be the case for k1 dot r? The k1 dot r we also split these components, k1 that is going this direction. So we can split this along y direction, along z direction. So along z direction we get minus k cos theta, along y direction we get plus k sin theta. So k1 dot r will be minus k cos theta into y plus k sin theta into z. So the total electric field after putting the values of k dot r and k1 dot r, we get E will be I cap E naught prime e to the power j ky cos theta minus e to the power minus j ky cos theta e to the power j kz sin theta minus omega t, where we are taking the common terms outside the bracket. Okay, and this is the common, kz sin theta is common for both the cases and omega t is also common for both the cases, for both the incident field and the reflected field. So we take this out and we are getting this kind of term, that is e to the power iota theta minus e to the power minus iota theta. So whenever you are solving this, you will get a sign of ky cos theta, and this will be as it is, that is e to the power j kz sin theta minus omega t. We are defining this, the after simplification we get the term as 2j e naught prime, and we are denoting this 2j e naught prime as e naught. So this is our electric field. Now look very carefully the form of the electric field. So whenever I am always suggesting you that whenever you are seeing any equation, you should read the equation carefully first. So E have two features here, one with the sign term, another with the exponential term. Now exponential j kz minus I am denoting this term because these are all the same. This is not clear here, omega t, that's why I am telling you this term, that is e to the power j kz sin theta minus omega t. It is denoting a wave that is propagating along z direction, okay, with a velocity omega by k sine theta, because whenever we are describing any wave and we describe it in terms of, suppose the wave is describing along x direction, that is positive x direction, with a velocity v, we will describe in the form of f of x minus vt, or it is going along negative z direction, we can describe the wave as x plus vt. So whenever you are going to understand this, you are understanding that this is k sine theta minus omega t, that is the k sine theta, omega by k sine theta is the speed of the wave and z is the direction. So this is the travelling wave, and whenever this term, that is k y cos theta, this is representing a stationary wave. I also have discussed that whenever in case of longitudinal modes calculation for the electromagnetic waves, that the electromagnetic waves is confined in a certain boundary due to these boundary conditions, that is the electromagnetic electric fields will be zero at the boundaries, magnetic fields will components will be zero at the boundaries, that will lead to certain boundary conditions, and that is defining our electric fields or magnetic fields, and we are getting standing waves, we are getting different modes, the modes of different numbers. Okay, so this is the our stationary mode, and this is our propagating mode, or that is propagation. Now the boundary condition we are imposing, I have already told you that I at y equals to 0 and y equals to a, electric field must be 0 for all values of z and t. So put this from this boundary condition we get sin ka cos theta equals to 0 for y equals to a. So ka cos theta equals to n pi. Now this is a very important physics here, that ka cos theta, that k is the wave vector or propagation vector. It is confined within certain numbers, certain integer values that will be decided from n. So we get discrete number of modes possible for the propagation of waves between the plates. So that's why we are getting different modes. Whenever you are confining it within certain boundary, the nature is not the transverse electromagnetic wave nature, which is like the electromagnetic wave is propagating in free space. The nature will be different, and it will be decided by certain properties. Now this is we have already told. Okay, now the next, go to the next slide, that is let us write the electric field. So the same electric field which we are confining, we are writing that sine kc as k cos theta and kg equals to k sin theta. So we write it, E electric vector is I cap into E naught sine kcy I e to the power or exponential j kgz minus omega t. So this is our stationary wave, and this is our travelling wave. So what will be the effective wavelength for the propagation of the disturbance, propagation direction, because this is the travelling disturbance, so it will be propagating along z direction with the effective wavelength lambda g equals to 2 pi by kg, because we are defining it as kg. So 2 pi by k sin theta, because kg equals to k sin theta. So 2 pi by k, if is the free space wavelength, that is lambda naught, it should be lambda naught divided by sin theta. Now the disturbance along y-axis, the stationary disturbance should be lambda c equals to 2 pi by kc, so 2 pi by k cos theta, or lambda c equals to lambda naught divided by cos theta. So we are taking two effective wavelengths, one along z direction, one along the y direction, and from these two wavelengths we are getting that 1 by lambda g square plus 1 by lambda c square equals to 1 by lambda naught square. So ka, since ka cos theta equals to n pi, we can also write that kc, k cos theta equals to kc. So kc into a, because from the boundary conditions we all know that ka cos theta we get that n pi, from the boundary conditions we are getting this, and from there kc into a equals to n pi. So we already defined or confined the wave vectors in certain modes, or kc equals to n pi by a, we get that. So 2 pi by kc, writing kc in terms of the wavelength, so 2 pi by lambda c into a equals to n pi, so lambda c equals to 2a by n. So the wavelengths are already also allowing will be allowed by certain n values, where n is discrete integer values. So the lambda will be also not continuously allowed. It is allowed with some discrete values. So the what is the physical meaning for a given n and a, that is the dimension of the planes, uh, or separation between the conducting planes. So lambda naught, if you increase lambda naught, then what will happen, at some, if you increase lambda naught value at some point when lambda naught is greater than lambda c, what will happen, lambda g will become imaginary. Now lambda g is the the effective wavelength which is propagating. Okay, so lambda g is imaginary means the propagation is not possible, because this exponential term that is responsible for the propagation of the wave, exponential j kgz minus omega t term, will become imaginary for z greater than 0. Or what will it represent? It will then represent exponential of negative term, means it will be exponentially damping term or exponentially damped wave in the z direction. So no propagation is possible. The waves will only propagate with a certain condition, that lambda naught should be less than lambda c, that is 2a by n, and this wavelength is called cutoff wavelength. Now we will find out the value of lambda g. Lambda g should be lambda naught divided by root over 1 minus lambda naught square by c square, or lambda naught by c whole square. From here we can get, okay, these are the simple calculations. And what will be the phase velocity? Phase velocity will be omega by k, in this case omega by kg. This is the propagation k vector, k sine theta, and we denote it as kg. So omega by k sine theta equal omega by k is c, so c by sine theta, or sine theta is less than equals to 0. So Vp is always greater than less than equals to 1. Sine theta is always less than equals to 1. So Vp should be always greater than equals to c, means the phase velocity is greater than the velocity of light. Now when theta equals to 0, lambda naught equals to lambda c, and this Vp tends to infinite. But don't worry, the phase velocity is going to be infinite. It doesn't violate the principle of relativity. Why? Because signals are always transmitted with group velocity. We will see soon that what will be the value of the group velocity. Before that, you shouldn't worry about the principle of relativity, because signals are always transmitted with group velocity. In the earlier video I have already discussed what do you mean by group velocity, what do you mean by phase velocity. Phase velocity is not the velocity of propagation of any physical quantity. It simply represents the velocity of a point of constant phase on the wave, and the energy also always propagate with group velocity. So you have certain disturbance in terms of the wave packets. The envelope that will represent the velocity, in which the envelope, the velocity of the envelope will be Vg, that is group velocity, and the individual phase, that is disturbance, that is the crest and trough of the crest or trough of the individual waves, that velocity is denoted by group velocity. Okay, now what will be the group velocity? Group velocity will be d omega by dkg, and what will be that? That is kg square equals to k sine theta, k square sine square theta, or k square 1 minus cos square theta, or k square into k cos theta, means n pi by a minus, so k square minus n square pi square by a square. So kg square will be omega square by c square in minus n square pi square by a square, because c equals to omega by k. Now differentiating with respect to kg, we get 2 into kg equals to 2 omega by c square into d omega by dkg. So Vg is d omega by dkg, that is c square into kg divided by omega, or c square into k sine theta divided by c into k, omega equals to ck, or we get c sine theta. So Vg equals to c into sine theta, that is group velocity is c sine theta. Now sine theta is always less than 0 or equals to maximum, it can be 1, sorry, not 0, is 1. Sine theta is always less than 1, equals to 1. So Vg is always less than equals, always less than c, or maximum it can be c. And another interesting point is Vg into Vp is from this relation, that Vg into Vp is c square. So this is the visualization that whenever electric field is confined in certain region or within the between the plates of conductors, the energy distribution is like this way. You can visualize it. Okay, in the next video lecture I will discuss the physics of the rectangular waveguide, and we will discuss some problems related to the topic. If you think that this video is helpful for you, please do share with your friends and subscribe to our channel. So for a review, what I want to remind you that whenever, because of the fact that you are confining or constraining the electromagnetic wave to move in a particular direction subject to certain boundary condition, a typical electromagnetic wave that is guided is not a transverse wave. In that sense we have learned. So however, even in the guided case, there are many certain occasions where you can have completely transverse electromagnetic waves, but due to the boundary conditions, that is the at the boundary the reflections, multiple reflections are happening, so we are getting transverse electromagnetic transverse electric wave, transverse magnetic wave, depending on the situation of the incident polarization of the electric field or magnetic field. So thank you friends. Tomorrow we shall discuss about waveguide, rectangular waveguide and related questions. Thank you.